Welcome back everyone after a short break, and we will start with our course. We will be starting with the first set of lectures, which are titled History of Ideas on Mountains, Tectonics and Geodynamics, followed by a talk on plate tectonics and orogenic cycle, paradigm and debates, followed by lithosphere definitions and the Earth's topography. Before I hand over the mic to Oliver, I'll just give you a very small brief introduction about him. We've already heard in the inauguration ceremony that he comes from the CNRS lab, the Geoscience Environment Toulouse, which is based in Toulouse, France. But Oliver is primarily from Germany. He has a German background. He is a full professor at the Paul Sabatier University, which is based in Toulouse. And I think, if I'm not mistaken, he's the deputy director of
Not
JET.
anymore.
Not anymore. He's finished his term there, but he was the deputy director at the JET. He finished his PhD in 1997 from the University of Minnesota in USA. And his topic was the role of partial melting during late orogenic collapse. He's been working on several research topics which are related to structural geology, analysis of pegmatites, geochronology on zircons and monazites, on several themes like the growth and differentiation of the Earth's continental crust, and etc. etc. So the details of that we will surely learn over the week. So I hand over the mic now to Oliver to start with his talks. Thank you so much.
Thank you, Malika, for this nice introduction. Can you hear me all, so I can avoid the microphone, so then I can move? No, I'm a tectonics, geodynamics person, so I need to move, and show things and be able to do motions. So that's the template for this week. And really what I want to share with you is my own thinking, but also put them into a context, a very large context in terms of history. I think this is something you need to do also as researchers, to try to understand where people were coming from. What was their historical concept, the mindset the people had at the time they did something. Because research is all about doing something different. You don't want to break everything and start from scratch. But if you want to do something different, you need to understand where people were coming from in order to identify what is robust and what needs to be improved. So this is what we will do this morning, and then we'll set up some kind of paradigm, but also identify questions about plate tectonics, orogenic cycle. And then we'll start with definitions. So that will be for this morning. Tomorrow morning I'll start the day with structural analysis of pegmatites, which is really what is my main expertise, I think. And I started when I was even younger than you. I was a bachelor student, I was thrown in pegmatite terrain of central France, and had no clue on how to deal with that. So I tried to develop an expertise that will help better understand what is the record of these rocks. And then we'll apply these ideas to the Alpine Himalayan belt and Tibet plateau. I think it's important to add Tibet to the picture. And that will keep us busy for tomorrow, Wednesday, Thursday. And we'll see different steps in the evolution of the Alpine Himalayan belt, with the Western Alps, Himalaya, Tibet, Aegean domain, and I'll develop that in the next few days. And then this will provide us thoughts and examples to nourish a thermal mechanical model for the evolution of Phanerozoic orogens from a stage of wedge mechanics to orogenic plateau and collapse of orogenic belts, relying on the mechanics, thermal evolution, and then combine both of them, thermal mechanical models. And then we'll see how this might apply to Precambrian cratons. As you guys we are here in India, and probably most of you are working on projects on India. Most of the Indian continent is made of Archean Proterozoic rocks, so I think it's compelling to you. and I'll open a gate here with how these thoughts on Phanerozoic orogens might apply or not to Archean Proterozoic cratons. Okay? I hope we'll... So don't hesitate to raise your hand, ask questions. I'll ask you some questions as well, so do not hesitate to provide answers. There are no stupid questions, no stupid answers. I'll start right away. What drives Earth topography? How do mountains form? What is your first click in your mind when I say that?
Collision of plate tectonics, tectonic plates. When they go like
Collision, plate collision, okay. And can you develop on that? Plate collision,
folding.
what happens? Folding, deformation.
Yes.
Deformation. Is this enough to generate topography? There are some underlying concepts. Isostasy. That's important. So we will see that actually plate convergence is so what you say, you know, when I ask the question for first year students, oh, mountains, it's like this. No, plate convergence is mostly like this. And then some isostatic rebound, right? So plate collision is like this, and then, right? So gravity is very important. And it's been, I think, forgotten for many years in tectonics and geodynamics. Okay, and what controls crustal differentiation? You know that the continental crust is made of an upper crust dominated by sediments, volcanic rocks, intruded by plutonic rocks, mostly granite. A middle crust made of metamorphic rocks, mica schist, gneisses, and then a lower crust made of granulites, mafic, and felsic granulites. And that's overlying ultramafic rocks, peridotites. Actually, I won't too much develop on that unless I decide that with our interaction is of interest to you. But I think this boundary, the MOHO, which is a geophysical boundary, is questionable in terms of its significance in terms of petrology. Now, I was in the field recently, and people would not agree where to put the MOHO in the field, where you had ultramafic rocks and mafic granulites, most of them. Mafic granulites, they're made of garnet, pyroxene, plagioclase. And their density is about the same as the one of ultramafic rocks. So the geophysical MOHO might be moving, you know, from mafic granulites to ultramafic rocks. This is a topic I'm not really sure I will develop on that, but that's something I think is something to be worked on in the next years. So what controls crustal differentiation? And growth and differentiation? Which geological processes you think might be involved in that? Mostly magmatic. Magmatic and metamorphic partial melting and melt segregation, migration, transfer, and at the place of magma emplacement, also segregation between crystals and melt. So what I proposed and developed this week is an integrated approach from lithosphere to mineral scale. So we'll deal with lithospheric plates, and we'll define that at the end of the morning. See how it behaves at the Earth scale, but then moves to structural analysis, and then link structural analysis to textures as the scale of minerals, and it's hard to read it here, but you have monazite, zircon, and you need to see where they are before you date them, and you analyze them. And in order to date them, it's important to understand their textures and textural position. You always get an age. If you do a laser ablation analysis of a zircon, well, you always get an age. You know? We'll give you a uranium-lead isotopic ratios, and this will yield to an age. What is the significance of this date, actually, we should say, in terms of age, timing of a geological event? is something very linked to your understanding of the textural analysis of the minerals and their textural position. If you don't do that job, you're not going to do crap. And even the best statistics is not going to help you. Statistics is going to help you to refine the age, but not to resolve the age. So let's start our historical journey. So we'll go from continental drift, which stipulated at the time from a meteorologist, interdisciplinary. Meteorologist, Wegener was a meteorologist. I think he looked at how the glacial, the polar, missed the word, ice caps behaved and how they moved, and that's probably gave him this idea. When he was doing research on the ice caps and was looking at ice breaking into pieces and then bringing it back to it, I think it probably gave him this idea. I'm not sure, but you can find his book. It's easy to find. It's a very interesting scientific adventure. And he said that continents made of aluminum silicates are drifting on top of the CIMA, the mantle. So we moved to plate tectonics in the 60s. That stipulated that what is moving is not only continents, but the lithosphere, crust plus lithospheric mantle, relative to the astronosphere, and we'll develop on that. We'll also look at the work of pioneers in geology, with Argan, a very creative geologist working on the Alps, and he reconstructed this tectonic evolution of the Alps, which was then reproduced in analog modeling, with a little bit of clay and sand and some kind of torque, which will produce that exact deformation. And at that time, what they gained from that is mountain form in response to horizontal shortening, deformation. And we'll move to float up tectonics. So you see that cork, that is plunged into water, and then what he wants to do is go up. So not much of anything horizontal here, right? Mostly vertical. Mountain formed by accretion of slab decoupled buoyant units. This is a concept that we're going to develop this week. And then Saint-Nectaire tectonics. Saint-Nectaire, you probably don't know what it is. It's a cheese from central France, which inspired me a lot when I was doing my first field work in central France. And you see it's kind of soft and weak. Mountains flow under their own weight. Gravity. Gravity, again, to construct and to destruct mountains. And that, I think, is even more compelling. It's compelling to phanerosic belts. We'll see that during the week. But it's also and even more compelling for Archean Proterozoic. Because the crust was weaker because the Earth was hotter. See, the reasoning is starting to build. So if we move back even further, in the 16th centuries, mining and geology started in Saxony. Really, mining started before, but at the time before, you just had to pick up the metals that were shining at the Earth's surface. But the understanding was needed after all the easy spots were discovered. Then geology came into play, and geology really developed together with mining. And that's the work of Agricola in Saxony, in Germany, nowadays Germany, with the Erzgebirge, which means metal-rich mountains. And they developed techniques to dig, to break the ore with fire, so they needed wood. And believe it or not, well, geology first developed with the analysis of veins, structural analysis, the cross-cutting relationships, because the ore were identified to be localized in veins. But then sustainable development was introduced right away by the guy that was responsible for one or two centuries later on of these mining activities. He said, if we continue like this, to break the ore with fires coming with wood, we will soon be out of wood. So we need to plant. We need to plant trees if we want to continue exploiting. Sustainable development didn't come the last 50 years. You know? It was right away. We forgot it, and now we are reminded that it's very important. The first Earth model, I like this one, Descartes, 1644. The world was made of, at the time he thought, sky, transparent matter, sun and stars, luminous matter, and Earth, planets and comets, dark matter. And for some reason, he put an internal fire at the center. What was his mindset at the time? Where the idea comes from, this internal fire? Volcanoes, right? Volcanoes. So imagine that there is something burning inside to feed these magmas. Put yourself into people's mindset if you want to understand their models and what is robust and not robust. And then there was an internal crust, solid and heavy and contains metals. Well, they knew that was where they needed to go to find metals. That was overlain by an external crust made of stones, clays, and sands. These are the sediments. And you see inside, in between these two crusts, there are water and air. This probably comes from cave exploration. You know, they could tell that if you go inside the earth, you find air and sometimes water. What I like is the next slide is, okay, how do you form oceans and mountains from this? Boom. You have the external crust is unstable and dried by the sun. It cracks and collapses, causing water expulsion from the earth interior to form oceans, owing to a primordial catastrophe. Here are the first mountains. The oceans is the water that is expelled out. I think it's lovely. You know, you don't want to do any anachronism with what they had at that time in terms of knowledge. This is fantastic in terms of creativity, right? Not saying that it's the way it works now we understand in the way we understand it now, but in terms of mind step, that's very very impressive. Descartes never went to the field. This was a philosopher. This guy was doing thinking. I think, so I am. This is Descartes. Huh? So he was not doing field geology, and actually the geology was, or these models relied on common sense knowledge at the time. So geology started just before with stratigraphy, with the work of Tectonics, Danish. And imagine by looking at that's the final state with observations. You probably recognize here discordance, structures. So imagine a model whereby sediments would deposit on top of each other, would be eroded from underneath, the caves, collapse, and then another series of deposits, then erosion underneath, collapse, and this is the repetition of discordances, unconformities. Another Earth model that came after the discovery of gravity, the gravity field by Newton, the one of Buffon. Earth gravity tells us that the Earth interior is not made of a fire. It's full of dense material. So there's no such thing as a fire. The Earth's round shape probably is a result of crystallization from a molten body, which gives it the shape of a drop. And mountains, well, in that time frame, in that mindset, might come from after crystallization of the primitive rocks from the molten body. As the Earth was cooling, it might have been shrinking, and with this shrinking, we might explain oceans and mountains. Again, that's marvelous. With the understanding that he had, it's marvelous. You know, I introduce more things based on more knowledge than the previous model. But again, Buffon was universalist. He was doing interdisciplinary science, biology, geology, and all sorts of things. It was too much for him to grasp everything. And in particular, geology was not very developed at the time. And it started to really develop when people started to do geological maps and cross-sections. And that started also in Saxony, in Bavaria, in Germany, nowadays Germany, with the first delimitation between different units, maps. And then the understanding of the relationship that you see on the surface is provided by cross-sections. If you want to do tectonics, structural analysis, tectonics, geodynamics, you need to do maps, cross-sections, I think. It's very important. Not only very detailed analysis of samples, put them into a context. From that analysis, they identify primary rocks, crystalline, without fossils, then secondary rocks, stratified, some derived from primary rocks by erosion, and some rich in fossils. And surface deposits, non-consolidated. So you can see here the beginning of the Earth scale stratigraphy. And this fed the thought of Werner. Actually, I need really here to apologize. My understanding of history of science and geology is mostly relying on Westerner world, because that's where I'm coming from. So if you guys have information about what Indians were thinking about these topics, I'm really curious to learn about it. I started to read about history of science at a larger scale than just history of Western science, but I don't find many reference to that. I'm really curious about how Asians would think about it, how Africans thought about it, South Americans, North Americans, before Western world discovered it. So Werner, so I have to apologize. Do you have any knowledge about history of science from India? Some? No? I'll be really curious. If you guys can send me references, I'm really happy to read it. So Werner, he built on the maps and cross-sections of Saxony, and he defined primitive rocks, granite, gneiss, schists, precipitated in primordial ocean before the formation of continents. And his idea was that all rocks formed by crystallization of minerals in the Earth's ocean, mostly water. So, and the time is going like this, linear progression of time, and irreversible processes. Primitive rocks, transition rocks, endured carbonates and detrital rocks, correlated at the Earth scale. That's very important. That's really the outcome of his work. Secondary stratified rocks, and tertiary alluvial rocks. Well, this has to be cancelled. That's from French. That's a relic from French. Alluvial, which is alluvial. And really the outcome is that he identified what we call the stratigraphic time scale that is still efficient today, used today. Primitive rocks, secondary rocks, tertiary rocks. Archean, Proterozoic, Paleozoic, Mesozoic, Cenozoic. We just changed the names, but the observation was there. And then he had to do some adjustment in his theory that with volcanic rocks. Especially in Saxony, you have these columns, basaltic columns, and they couldn't ignore that there was some volcanic rocks, and volcanic rocks didn't form by crystallization of minerals in an ocean. And magmas, you can see them put and placed at the Earth's surface today. So he put that at the end of his work. Magma erupted from volcanoes, but that was not in the original work. So his mindset was so strong that he managed almost all his life not to incorporate volcanic rocks in his model. So in other words, when you're going to move forward, you don't want to be too strong-minded. You need to incorporate things that even are not fitting your model. At the time, there was a debate with Plutonism and uniformatism that introduced the rock cycle, Hutton is often cited, quoted as being the one that is responsible for that. Or if you read Hutton's book, it's very difficult to understand. It's written something totally different from what the style we have now. Anyhow, he identified clearly the unconformities, developed on that after the work of Tectonics. And you see here rocks that are banded with folds, metamorphic rocks, schists, separated by a layer of soil from sediments that are unconformably overlying the metamorphic rocks. So he identified that these rocks were former sediments that transformed into rocks owing to heat and pressure, metamorphism. Rocks then uplifted to the surface and then are transformed by weathering and erosion to sediments. And this introduces the rock cycle, up and down, up and down. The first trip to the Alps, well, mountains were sort of left on the side because it was difficult to climb on mountains, you know, at the time. And look at how these guys went with sticks, you know, carrying a lot of material, almost like they were almost going like we are with the clothes we are wearing here today, right? So imagine the challenge to go up on the mountain that is not the Everest, but it's still almost 5,000 meters high, with a lot of glacier. And this guy, de Saussure, he sort of put a challenge to the people of Chamonix in the Alps and say, okay, I'm going to give some good reward to the first one who's going to find the path to the Alps, to the top of the Mont Blanc. And this guy was a geologist. You see his hammer, a compass, and then all sorts of material to measure pressure, temperature, and humidity. You know, he was doing a lot of things. And among the things that he discovered was from the foothills of the Alps, folded limestone. What can you tell about folded limestone? What is the message?
That it used to be a marine area. It used to be part of ocean.
Yeah. And you here, so continue, follow up on that.
He got subducted with another plate after collision, and as a result, it was subducted.
Yeah, so you have some knowledge in there, because you take anybody and show the fold limestone, say, okay, it's a rock, you know? But you have knowledge. You have knowledge that this is marine rock, deposited at the horizontal. And it's folded now, so it means that it's been deformed. So what I want to get you there is that you put your knowledge in order to build a model. This knowledge allows you to elaborate an initial state that you compare in your mind with the final state. And us as scientists, we need to, if we want to test the robustness of our models, to really rebuild all these stages between our knowledge and the final state, which is what everybody is seeing out of this room. What is our input? So structural geology of crystalline rocks continued. This guy is named Durocher. In French, is from the rock. So he had the right name to do it. So he identified folds, different type of schistosities that are folded several times, budines, and that's all from the Armorican Massif in France, Western France. Cornwall in southern England was also a big place for development of geology. They identified the relationship between bedding and cleavage, granitic veins, intrusive into metamorphic rocks. We'll come back to that tomorrow morning. And this was also a place where there was big exploration for ore deposits, coal at first, but also iron, and that participated in the development of the industrial revolution. And that's not. It's not by chance that these years are connected with the Industrial Revolution and geology development. This also brought people to look into the rocks, and I was surprised to realize that the first goal to look at rocks under a microscope, but was to find water. They were not looking at minerals at first, they were looking for water, because they wanted to test this hypothesis of Werner and Hutton, if rocks are all coming from water. So, they found water inclusions. Werner is right, it's all coming from water, deposition in water. We have different interpretations now, but the observation is there. And then they look at textures. On here, garnet and andesite schist in the Alps, granite, magmatic textures, metamorphic textures. And that came with the development of technology, of microscope technology. So it's also, our understanding, knowledge is also tied up with technological improvement. LA-ICP-MS, with LA-ICP-MS you can go one step further in terms of the precision of analysis. Contact metamorphism, so that's moving. Next step is to try to integrate. I don't have the time here. I mean, I'm not sure how I'm doing, so I don't know when I started. 10:30? Okay. Okay, I'll move a bit. So then try to understand now what these textures and minerals meant. And at first was contact metamorphism, what that was identified in the Vosges mountains, at the border between France and Germany, with cross sections. That's the road. So that's outcrop description, cross sections, and mineral description with textures. We would call now these textures porphyroclasts, porphyroblasts. So this was identified at the time, with here internal structures in the minerals, and the same was shown here as minerals in an aureole around granite. That's a granite. This is metamorphic rocks, and here there's an aureole with andalusite that was overgrowing the previous structure, and they interpreted that as contact metamorphism. And everything was set to build that very nice schematic representation of relative chronology by Lyell in his book of 1857. There are some things that are not possible here. I give that, maybe Malika will give that as an exam to students. And I would say for first year students, you take only this part and try to identify all the events by order. But for more advanced, try to sort out this part. And probably I found it paradoxical. There are some things that are not geologically possible with our understanding. So either he made a mistake, or we don't know enough to understand that. Regional metamorphism was another way to explain metamorphic minerals by Barrow in Scotland, where he identified different zones marked by the presence of different minerals: sillimanite, kyanite, garnet, biotite, chlorite. And he identified or defined the metamorphic isogrades with their relationship with structures, folded bedding and cleavage. And this now fed the first maps, large-scale maps, in northern France and southern England, with the mineralogical map first, so the presence or absence of minerals. And you start to see here geological units. That's France. And here myself, as I know geology of France quite well, I recognize the Variscan Massif, the Paris Basin, the Aquitaine Basins, the Pyrenees, the Alps. Everything starts to show up on this map. And that started from minerals and then rocks. The first geological map at the scale of a continent or part of the continent is the one of Eastern North America by McClure in 1809. Short after came the one of England, 1815. And that's where most of the stratigraphy of the Paleozoic has been built up. And you see also the use of chronostratigraphy with fossils that were recognized to be symptomatic of different sediments, and the nice cross-sections showing the relationship between all these rocks. The one of France came about 30 years after, and they used that stratigraphic scheme provided by Werner with the transition, Jurassic, Cretaceous, Tertiary was all identified at the time. Also cross-cutting relationship between sediments, or the basement, folded sediments, stratified sediments and veins, cross-cutting them. And this served to build a cross-section at the scale of the Pyrenees. So that's where I come from. No, Toulouse is somewhere here. And this is remarkable. You see here the Miocene, so that's a cross-section like here. So you see the Miocene unconfirmably overlying the Mesozoic, that is overlying the Paleozoic, and in the center you have the gneisses of the internal massif that are exhumed. After the map of France came the map of Germany, and you start here to have a way to build the map of Europe with a consistency in colors. And this color scheme is the one that is still in use in most maps. So that's also something I want to insist in. No, I'm not sure if there are geophysicists or geochemists in the room, but no, Malika says, so I can speak freely. I hate the maps where the colors are just jumping to each other. If we have a common language, it's a common color scheme. If you use colors that are nice to you but are not understandable to each other, to other people, that is, we need to speak the same language. So if I see green, I know it's Cretaceous. If I see purple and pink, I know it's metamorphic gneisses from the basement. It comes right away to my brain. Geological map of India. I didn't find the author other than the Geological Survey, but it was done in 1877, so you recognize the Deccan Traps, most of the Archean Proterozoic basement, the Himalayas. It's kind of nice. The high Himalayas were difficult to reach, obviously. And from that time, it was also the time of well-scaled geological maps with the same scheme. And that's remarkable. To do that type of synthesis is remarkable. We can identify the Archean Proterozoic cratons, the different orogenic belts, Urals, the Variscan, the Alps, the Cordilleras, everything is there. And that fed thoughts about regional scale geologic tectonics thinking, with here the work of an Austrian, Suess, that identified the different tectonic belts. The oldest one is the Caledonides, that affects basement that is before the Carboniferous. And then what he called the Altides, that continues in Asia, and that's what we call now the Variscan. And then the Altides posthumes, which are the Alps. And he thought that these were close to each other in terms of timing, and they almost follow each other right away. The work of a French guy, Marcel Bertrand, who also went to North America and identified there was a continuity of these belts across the Atlantic, which was not obvious, to try to find. So he called the Hercynian and Caledonide belt, find their traces in the North America. So now, how these data fed models for mountain formation? Well, at first, after the ones I showed you before, the collapse of a dried crust and the shrinking of the Earth, it was thought that maybe magmatic processes would come into play with the build-up of mountain belts, and it's taken here from Fambourg German guy, that looked at the chaîne des Puys in central France and saw that each of these mountains was a volcano. So he thought maybe that's the process that builds mountains. This idea was sort of developed by Scrope, that here related the exhumation of plutonic rocks, gneisses and granites in the central part of mountain belts to the formation, the rise of uplift of the surface and glide of cover rocks, sedimentary rocks that form folds in the foreland. So here the folds are not related to, in this model, not related to horizontal shortening, neither to convergence. And we'll come to that later on, define all these but the idea was also very, very interesting, that you have a uplift here and then glide of units from the central part to the outside. Earth cooling shrinking was modeled with an inflatable balloon. He tried, Dobré drew some lines on it and looked at what happens when the balloon deflates. And this fed the idea that earth cooling and shrinking could lead to pentagonal mountain system, why pentagonal and not hexagonal or strange. But Élie de Beaumont, who was one of the guys that did the French map, geological map, thought, okay, maybe pentagonal. So he drew great circles on the sphere, and he thought they could match the different belts he had mapped in Corsica, Sardinia, Western Alps, and Central Alps. Where you see here all the unconformity between the tertiary rocks, secondary rocks, primitive rocks. Experimental deformation also allowed to reproduce structures observed in rocks, and that gave the idea that here we can monitor the amount of shortening. So that gave the idea of balancing cross-sections from sediments. Try to retrieve their original state before deformation, and then evaluate the amount of shortening. Another type of model that was very popular in the early 20th century is the geosynclines. It was identified that rocks were deformed specifically in zones with a belt-like shape. That Seuss has also identified that. And the idea was that maybe that was not related to shrinking, but maybe to the weight of the sediments that would cause sinking and subsidence and then shortening. Well, this is the cause and effect is sort of included in the cause is included in the effect. This implies that the trough, the space for the sediment deposition, is created by the sediment. So it's kind of a paradoxical relationship. The sediment says, I want to deposit here, so I'm going to create my space. It's kind of a logical problem, I think. You need to have space that is created before the deposition of the sediments. I think it makes more sense. Anyway, that was also a way to explain the zonation of different belts. In terms of Earth internal structure, so geophysics, gravimetry, seismology, allowed to have a first idea of the Earth interior, and comparing these signals with meteorites allowed to build another more refined Earth model with the identification of that there is a dense nucleus made of nickel and iron. And that's basically based on the identification of the iron meteorites that have the right density and the right behavior in terms of seismic wave propagation to be in the Earth interior. And then a mantle made of silica magnesium, the SIMA, and the Cial, the crust made of silica and aluminum, mostly. And that brings us back to continental drift, which was built mostly on geological evidence from the continents. The oceans were almost unknown at the time. So you had geologists were much in favor of that. based on sedimentary rocks and fossils correlation across continents, crystalline rocks, glacial deposits, structures across continents. See here a reconstruction with also the cratons and the Archean cratons nucleus and the Proterozoic belts across the Atlantic and the fit between the coast of South America and Africa, West Africa. So geologists were much in favor of that, and also the need to find ways to explain the large horizontal motion. And this was also nourished by the identification of metamorphic nappes, which also led to the zonation of mountain belts. And here the example of the Variscan belt with a foreland made of sediments, a zone of intermediate Rheno-Hercynian and Saxo-Thuringian made of deformed Mesozoic, and not Mesozoic, deformed sedimentary rocks, and then the internal zone, called here the Moldanubian, made of metamorphic rocks and plutonic rocks. And as these were identified to be, for example here, the Moldanubian internal rocks were identified to be overlying the Saxo-Thuringian rocks in the external zone, that led to the idea that there was a need for large horizontal displacement. And these guys were in favor of continental drift. Argan, who also was a supporter of continental drift in order to explain the formation of the Alps between moving continents, but also the Variscan belt, that's just along the same trend as the Alpine belt. And he was getting crazy here. No, I'm not. We just take a minute to read that. The strong axial exaltation was marked in the Hercynian times in what was to be the Massif Central of France. It seems that no fact is sufficiently disturbing to prevent us from tasting on those rafts where our destinies float. The delight of the wise outburst to which Mr. Wegener invites us. We're not writing science like this anymore, right? But it was inspiring, I think. So I'll leave you to that now, before a short break. Geologists, most of them, were in support of continental drift, but geophysicists said, okay, okay, but maybe we need motion, but it doesn't work. The Cial is on top of the Cima, and the Cima is the strongest Earth shell. So how come the Cial could deform the Cima so easily and move on top of it, like if it was floating on top of water? Be careful, I'm going to trick you on that today, at the end of the morning. You're ready? So the guy, Jeffrey, an English geophysicist, says there's no way. And the force you are invoking, Earth rotation and the centrifugal force, the Coriolis force, is not enough to move such big bodies. What is strange? So we need a driving force for continental drift. What is strange is at the time of continental drift by Wegener, 1912 is the first version, 1929 the last one. Well, the lithosphere had already been described. Barrel, 1914, is the first one who talks about a lithosphere based on the isostatic rebound of the Scandinavian continent after melting of the ice cap there. And he measured the rebound by measuring displacement of hooks for boats. They were identified on the coast of Norway, the Drakas from the Vikings, and you could find hooks very high on the coastline. So it allowed to measure uplift of the coastline through time. Amazing, huh? So in this way, he measured the elastic rebound of the lithosphere. He identified that there is some kind of a strong layer, the lithosphere, sphere made of stone, compared to a much weaker one underneath that is allowing for this rebound. The geodetic evidence of isostasy points towards the existence of a thick and somewhat plastic zone beneath the more rigid lithosphere. So Wegener didn't use that, and that's too bad for him, because he had everything at the time. But we'll see in the next hour how we can use that to link with the mountain belt formation. So if you have any questions, thanks for some of you participating, but you also can ask questions if there are things that are not clear or inspiring with you. Yeah?
In this figure, what is this M and N?
M, N. I'm not sure. You can find these papers fairly easily. Barrel, lithosphere, you can find the papers and all the mathematical development of that on the internet.
Sorry if I missed something. So in this figure, so are they just showing lithosphere as a part of continent only here?
Yeah. Over?
Lithosphere and astrosphere only as a part of continent here? Or
Yes. Yeah, M and N might be different continents. That's possible, but I'm not sure. Maybe there are different, laterally different type of continents, and that might be the. It might be somehow illustrating here the Scandinavian relative to the Atlantic. I'm not sure. That's what is your question, huh? Maybe that's relative motion between different part of continents or Earth's surface, I would say. On other slides? Okay, let me just ask you if, because I know the public is very heterogeneous. Okay, who is a PhD student here? Or maybe PhD, a faculty member, one, recognize the older guy. And the other ones are bachelors, first year, second year, third year, third year, masters, sorry, masters, third year bachelors, second year. Is it first year also? First year? Is it okay? I mean, for you, yeah? No, so. Because it was difficult for me to adjust the presentation to this very large audience, from first year to faculties. So I hope everybody is going to get a grasp on or take something out of it. And this was the easiest part, the history, right? So then it's going to be a bit more challenging. So do not hesitate to ask questions, and stop me if there are terms that I use that are not understood. Okay, so we'll take a short break. Is okay, Malika? Good timing? How am I doing for timing?
Yeah, good. So we break 5 minutes. Are you?
Yeah.
First,
First, yeah, sure.
break 5 minutes and come back.
just
I'll let you do it.
This switch.
So you confirm that the microphone is working? Yes? So let's move now to the second part of the morning, plate tectonics and orogenic cycle. So we move from continental drift now to plate tectonics. And plate tectonics was really put together in the 60s of the last century and was built up from geophysical data on oceans, exactly the opposite as continental drift, which was built on geological data on continents. And it stipulated the lithosphere, crust plus lithospheric mantle, so the upper part of the upper mantle, is subdivided into a dozen plates that are moving relative to the asthenosphere. In some places, plates are diverging, and this corresponds to mid-oceanic ridges, and it's causing thinning, extension. We see, I'm going to use that word, but I think it's very confusing, and I need to define exactly what I mean by that. And sometimes in the literature, you'll find it's used in different ways. Plates in other places converge relative to each other, and that is accommodated by subduction. Subduction being the motion of a plate beneath another. But really, plate tectonics started a bit before that. The 60s have been highlighted as a historical moment where geophysics and geology came together. But there was a brilliant guy, Holmes, that set up all the evidence before the 60s. And first he realized, okay, if we rely on Earth rotation as the main driving force for continental drift, then the dominant force available tends to set up a westerly drift due to tidal action, and a drift from the poles towards the equator due to departure of a polar section through the Earth from a circle. So basically he said, okay, when we look at the present day mountain belts, they're not consistent with that. So we need another force. And this other force, radioactivity, has just been discovered a few years before, and the radioactive content of rocks was also identified at the time. So he sort of evaluated the thickness of the mantle, its content in radioactive elements, basically uranium, thorium, potassium, and he calculated the viscosity or the temperature of these rocks, and then their viscosity as a function of the radiogenic content. And he says, well, that's consistent with this mantle to be gravitationally unstable and to be activated by convective motion, convection. Convection currents may be set in the lower layer as a result of differential heating by radioactivity. And this is his representation of upwelling, downwelling, and represents Gondwaland, Tethys, Laurasia, North Pacific, South Pacific. Everything is set here for the large-scale picture. And at the same time, he applied that to use the knowledge of lithosphere. And you see here a continental block on top or laterally connected to an old ocean on top of something that looks like a lithosphere, the mantle lithosphere. So he identified the lithospheric plate. And he says the effect of compression on gabbro would be to transform the material into eclogite. Eclogite, for the bachelor students, is a rock with garnet and pyroxene, which is quite heavy, quite dense. Such a change of density and the simultaneous action of isostasy would lead to the formation of oceanic deeps, trenches. So I identified, so these crosses are eclogites. These are the places where the lithosphere goes down because of its weight. Remarkable. And he also put mountain system in there as places where the downwelling occurs. So that's, I think, the first steps for plate tectonics and mountain building, orogenic cycle. So nowadays, plate tectonics or lithospheric plates are identified thanks to localized volcanic activity around the Pacific, but also along the Alpine belt, so it's not as well organized, and also along rifts, such as here the East African rift. There are other places where there is volcanism, which is not really mentioned here. It's all along these ridges, there are lots of magmatic activity. And some hotspots, Iceland, Hawaii, places where there is localized magmatic activity, volcanoes that are not completely linked to plate tectonics, such as Hawaii. Iceland is on the ridge. There's also localization of earthquakes, earthquakes with different depth of their hypocenters. Depth that is here indicated by colors. Red is the surface. Well, let's just think that might be also an exam question. Describe the distribution of earthquakes, integrating also the color scheme for depth of the hypocenters, and identify the different type of plate boundaries. So I'll let you think about that just 1 minute. Look at the colors. How are they distributed? How are these mid-oceanic ridges in the Atlantic, Indian Ocean, Pacific? How are they distributed? Shallow or deep earthquakes? Shallow. Shallow. So diverging plate boundaries are characterized by shallow earthquakes, less than 30 kilometers. And then if you go along the Pacific, what do you identify? Colors are changing. Red, orange, yellow, green. What does this mean? Subduction. Subduction, and you can identify the polarity. And there's the polarity, it's deeper towards the west here, so the plate is plunging towards the west. So we see that along the Pacific, West Pacific, East Pacific, same thing. So if you have an oceanic plate converging towards a continental plate, same thing happens. So there is subduction there too. But here, the polarity is towards the east. What about the Alpine Himalayan belt? Alpine Himalayan belt. What happens here? Type of earthquakes. Mostly shallow, but there are lots of shallow earthquakes that are distributed. It's not as restrained in space as along oceanic plate boundaries. So it's distributed in space, but there are some deep earthquakes there that are also kind of hidden below the red ones. So what does this mean? How would you call that type of belt? Just spontaneously. Alpine Himalayan belt. Continental collision. That's, I think, the most common way to describe this. What are these deep earthquakes telling us? More than 100 kilometers. Might be crustal, but we'll see that from geophysics, we do not find evidence for having crust as thick as 100 kilometers.
It's not as thick, it's just like yellow, right?
Yeah. 150, it's 150, but it's difficult to read from where you are. So we have here earthquakes that go down to 150 kilometers, and especially here, here also, here. Here it's not identified, but it's also the case. What does it tell us? Suture zones, and how is plate convergence accommodated in these places? If there are earthquakes as deep as 150 kilometers. Subduction. So it's a subduction collision belt. we start to have a problem here of terminology and concepts. But we'll clarify that right away. So these were used, these geological evidences were used to define the first lithospheric plates in the 60s. And that leads to the scheme that is here reproduced from a figure from the Geological Survey of the States and of America. That's an interesting one. Look at the Eurasian plate, North American plate boundary. Well, see that Kamchatka and part of Siberia is North America. Huh? If you thought that you were doing neutral science, this is highly political. Where do you see the evidence for a plate boundary? In terms of seismic? In terms of volcanics? If I had to make a choice, probably we'll put it here. You know? Very politic. Nobody cared about this place of the world, 20 years ago. But now it's a very touchy place because thanks to climate change, the ice is melting, right? So all these new continents, shelves are going to be exposed, and there are lots of resources. It's a place where you can also travel, from one place to the Earth of the Earth to the other. So they are very, very important. So I think we're going to play an important role just at delimiting plate tectonics. And we're going to be asked soon, okay, does this place belong to Russia, China, or North America, or, You'll see.
So, in the earlier slides, if the subduction is occurring, then shouldn't the yellow points be in a greater number and in a linear fashion along the plates? There was
Start again.
You told that the yellow points,
yes,
they were due to subduction, right?
Yes.
But there are a greater number of red dots along the area.
I know.
If subduction is occurring, shouldn't there be more number of yellow points in a more linear arrangement?
Yes, you're right. So this is a what you're saying is that there is not an alignment of these yellow points all along the belt. Huh? This is correct. Huh? But that's I think it's 5 years of record. So they are not as the recurrence is not as great as in the ocean continent subduction, but they are there. How continuous? That's also a question, and we'll see that in the next few slides. But it's a good question, I think.
So my question is somewhat contradicting to this. So what I asked is that even if there is subduction, so how are there so many earthquakes possible below the thermal LME?
Next slide. We'll see that. No, but I think I put some kind of seed in your mind, and it's growing. It's good. But that will come at the end of the presentation. First, we start with the basics of plate tectonics, and you asked me for that. Huh? And well, it started with the middle of the oceans, birth of the ocean at mid-oceanic ridges. I started with I didn't put the slide, but with the topography of the ocean was reconstructed first with a cable that served for telegraph. So that was taken from Europe, London, and Great Britain to New York. And they went with a ship and left the cable going down to the ocean floor, and then all of a sudden, in the middle of the Atlantic, they realized that they didn't have to go for 4,000 meters, but only 1,000 meters. Oh, there's a ridge there. So that was the first image of the mid-Atlantic ridge, was because of the cable for telegraph. But then it was improved a lot, thanks to the Second World War, right? Because many ships were there trying to find submarines, so they measured bathymetry, and they measured magnetics, identified the metals. lots of knowledge, unfortunately, comes from war and armaments. We know that. And most of our scientific knowledge comes from that. That's a pity, I mean, from my point of view, but that's the way it is. It's a luck that some people from these, especially here the American Marines, they thought, okay, now the war is gone, is finished. What can we do with this data? So they managed to use this data to build the bathymetry and the magnetic anomalies of the oceans. Here it's a seismic wave velocity image, so it's difficult to read, but you see here that there is a less rapid material beneath the mid-Atlantic ridge, and that was discovered by Ewing in the late 50s. Here the magnetic anomalies. So at first, the record is not as, that's the original image from Vine 68. All these now with the internet is easy to find. So if you take just the reference and you put the correct words like magnetic anomalies, you find this. So this is how they look. Here that's close to Iceland along the mid-oceanic ridge of Atlantic Ocean. So from that repetition, he had black, white, black, white, black, white, centered on the Atlantic Ocean. They reproduced, that's the average magnetic field. And so I took that from a sort of general textbook, and you had some places where it was above, below, above the average magnetic field. And that was interpreted as being related to trapping of the magnetic anomaly, magnetic orientation at the time of crystallization of the basalt that forms the ocean floor. So you see this black vector going up or down in the red and white stripes. And this is really magnetite minerals that are in the basalts and are oriented at the time of cooling of the basaltic magma, in the orientation of the magnetic field. And what they identified was it was either pointing towards up or down, but with the same direction. And that's up, down, up, down, up, down. So the idea was that in between the emplacement of that basalt in white and which is now here in the next step, and this red basalt, there was an inversion of the magnetic field. And by this way, we can reconstruct, by dating all the inversions, we can reconstruct the expansion of the ocean from the mid-oceanic ridge. Divergence, thinning will lead to, so I'll do a shortcut here, will lead to decompression of the mantle underneath, and decompression leads to partial melting, generate a basalt that is placed at the surface to form the new crust. And then divergence again, this new crust is separated in two. These two stripes that formed only one here are there. And then another event of magma extraction occurs, but in between there has been a switch or reversal of the magnetic field, Earth magnetic field, and so on. So this was for birth of the oceanic lithosphere and crust, actually, but we'll see how the lithosphere behaves. And then what happens to it? Well, it's being recycled along convergent plate boundaries marked by trenches, such as here the Mariana Trench in the Western Pacific. And the process here is one plate goes beneath the other, and it's identified, illustrated by the depth of hypocenters. So that this is the Mariana Trench here. And you see its shape, that's a map view. And we're now going to see cross-section views that are here. So here you have the distribution of the hypocenters of the earthquakes at depth, which are called the Wadati-Benioff plane, because there are two persons that developed that, made that observation. Wadati, who's guy from Japan, no surprise, was very concerned by earthquakes. Benioff is German. These guys are not much concerned by subduction, but in Germany there is a history of technological development. So it also explains why they made that type of discoveries. That was part of your question, the distribution of earthquakes. So you see here there's a diffuse zone of earthquakes on both sides of the plate boundary, and there's a localized zone of earthquakes which delimits the plate that is going down. So it's both. You know, you have long convergent plates, you have diffuse zones of earthquakes and deformation at the surface, but also localized at depth, with some holes in there. So there are some things that are happening. It's not a continuous process. And we'll not see it, but it's probably related to metamorphic reactions, water release, and the behavior, who was asking brittle ductile behavior of plates as they transform into minerals related to metamorphic reactions. So we have seen birth at mid-oceanic ridges of oceanic crust and lithosphere, recycling along subduction zones. Now plate tectonics needed a mathematical model that came from Euler. Euler is a German mathematician who studied all sorts of problems, not particularly geology, but he proposed that, he elaborated that plate motions on top of a sphere are defined as rotations with an axis that goes through the center of the sphere. And this has been applied then to plate tectonics. In this case, the motion of one plate can be defined as one single angular velocity vector. So that's the beauty of plate tectonics. It's very simple. But it requires also that plates move like this, opens. So it opens like a scissor with a maximum opening along the equator of relative to the axis of rotation and 0 at the axis of rotation. And this doesn't take into account the recycling along subduction zones, only opening. So what happens here? Does this really account for the features we see along tectonic plates today? Not really, not exactly. We see this scissor-like opening, but we don't see a continuous zone, a boundary like this. What we see in the Middle Atlantic, for example, are transverse faults that are cutting across the mid-oceanic ridge. And these transform faults are transfer zones. Here's the San Andreas one that is going here from the mid-Pacific beneath or intersecting with North America. That's San Andreas. San Andreas is here, San Andreas fault. And you see there are mid-oceanic ridges are represented like this, and transfer faults are like that, perpendicular to the ridge. That's the one in between the Arabian Peninsula and Africa, with same ridges, transfer faults. So that's a schematic representation by Isaacs, 1968. So all happened in 1 year. All these were put together in 1 year. The subduction, opening of the Mid-Atlantic ridge, and so on. So if you see a ridge like this, another ridge like that, and a fault in between, what kind of earthquakes do you expect here, and what kind of motion do you expect in between these two segments? So we're going to vote. Think about it. Is the top part moving towards the left or moving towards the right? Be careful, there's a trick. I'm not going to make you vote because I don't want to make you feel uncomfortable. But first, the logic was, okay, this has been moving towards the left, it's been offset towards the left. But the earthquakes that were identified along this zone were all indicating the opposite. And that's why it's called transform zones. Because really what it does, it accommodates differential opening along different segments of the mid-oceanic ridges. So here it's opening like that. Here it's opening the other way around. So in between, the motion is like that. But it took them a while, At first they were thinking, oh, that's strange. Maybe we made a mistake in our interpretation of the earthquakes. So it took them a while and then they understood it. The question now, I think, which is still unresolved, is why these transform zones, well, let's put it another way. That means that this ridge was never in continuity with this one. Why isn't this the case? In this scheme, there's one ridge. And we understand that differential opening might be accommodated by these transfer zones. But why is the ridge offset? That's a question for you guys in the next, for the next PhDs. I'll put you some ideas to work on. Probably has to do with the distribution of cratons, hard spots. Where the weak spots are, where the hard spots are, is going to control where the geometry of opening. We're not opening an homogeneous Earth. It's opening with lots of heterogeneities that are going to control the place where the offsets are going to be localized. That's another question here. This is nicely drawn. It's taken from a picture which represents mid-Atlantic, the Atlantic, North and South America, Eurasia and Gondwana, or Africa. And here you see that the axis of rotation is not totally random. Can you see something? Malika? It's almost coincident with the Earth rotation. And it's been killed in the egg. Wegener proposed that Earth rotation was a force controlling plate or continental drift. But the geophysicists said, oh, that's too small. As a geologist, I think there is something there. We'll come back to that later on. So these transform zones are necessary to accommodate differential opening of oceans and also differential subduction related to the fact that motions of plates on top of the sphere are rotations. And the shape of these transfer zones, they are slightly accurate and corresponds to big circles in the stereographic projection, big circles. So the curvature was used to identify the pole of rotation. So what these guys do, Isaacs and colleagues, in the 60s, they identify all the transfer zones, drew lines perpendicular to it, and saw where they would connect and identify the poles. That's how the first poles were identified, poles of rotation. And then they measured displacement relative to the ridge and identified that displacement was symmetrically decreasing from the, not from the ridge, from the pole of rotation, was the motion was symmetrically increasing relative to the pole of rotation. So our first pole. Second way to identify the poles is to use the poles recorded in rocks on the continents that show an apparent polar wonder. For example, if we measure a pole trapped in Eurasia, in green here, in rocks that are 500 million years, the pole was here. If you measure the same pole 500 million years ago in rocks from North America, it's here. So it shows an offset. at the time where there are two poles, two magnetic poles. So that's the magnetic pole, not the rotation pole. Huh? I changed topic here. Today, if we measure the pole, it's the same place for both North America and Eurasia. 100 million years ago they started to be offset, more offset 200 million years ago, and even more as time proceeds. So either the pole was wandering and was not the same for North America or Eurasia, or another way to explain it is to move the continents and make the pole match and the continent move. Instead of having the poles moving, make the continents moving and match the poles. And that leads to that reconstruction 500 million years ago and opening of the Atlantic in several steps. So we now have all the tools to reconstruct plate tectonics. We can identify with the transform folds the poles. We can then have a model of plate motion with the transform folds with the axis of rotation. We'll come back to that. No. We can also measure the displacement along mid-oceanic ridges by dating the rocks on each side of the mid-oceanic ridge. And this was done since the years. It was done throughout the years. And this map, it really reflects, you can see all the different rectangles. Each rectangle corresponds to a magnetic anomaly, black or white, black or white. So these are only binary maps, black, white, and the colors have been put by ages. And if you look at how many ages we rely on, it's not that much. There is one section here, maybe one here, and there are also one or two sections in the Pacific where the deep drilling has allowed to date rocks. So this is really a conceptual model that relies on a few data. And it's really binary. And with binary reasoning, if one step is wrong, boom, everything falls down. Huh? So I think that reflects, it's very simple, it's very nice, but it reflects the lack of data as well. Nevertheless, we have a map of age going from red, 0 to 200 million years in blue, and you see the symmetric distribution of colors, ages relative to the mid-oceanic ridges. And for the Atlantic, it's very nice. It's very nice, symmetric. The oldest are on the margins, the North America and Africa margins. And we can reconstruct the opening of the Atlantic, first here in the central part, and then move towards the northern and southern parts, and then finished with the northern part. This continued that this was like this, and then like this. Very symmetric. And there's no subduction on the margins here. So that's why the symmetry is well preserved. In the Pacific, the symmetry, let's take we'll finish with the Indian Ocean. The Pacific, we see that symmetry here, fairly well preserved, but starts to be unbalanced here with an very old lithosphere along the Marianas. That's where it's very deep, steeply plunging. Whereas here, the ridge is going into subduction. That's a strange, peculiar feature. That's not explained by plate tectonics, by basic plate tectonics. So we come back to that. So there's strong asymmetry here. There's a strong west-east asymmetry. So the Atlantic opening is consistent with an axis of rotation, almost coincident with the Earth rotation axis. And the Pacific, for this part, is also well organized relative to a north-south axis of rotation with a strong west-east asymmetry. So there is kind of a west drift, something that goes with west-east asymmetry. So in order to reconstruct plate tectonics, we need a reference frame. And that's something tricky. What is fixed? Everything is moving. So how do we measure? We measure relative displacement across plate boundaries. But can we measure absolute motion? Very difficult. So at some point, they thought maybe the hotspots, the volcanoes that are not related to plate boundaries might be fixed, and these strands might record the motion of the plate relative to a fixed point. And these are the hotspots represented in that figure. But by doing that, it works, somehow it works at first order, but then we see that also the spots are moving relative to each other. So it's not that fixed. Finding a fixed reference frame is not something easy. So the principle here is that if we look at Hawaii, the active volcano is here, and as you go along this strand, these are old volcanoes, and the oldest is subducting here. So you go younger, younger, younger. Here there was a kink in plate motion, sometime during the Eocene, close to 60 million years, and then a regular trend. So the idea is that the hotspot is related to melting of the mantle, but at depth, very, very deep, not as in the oceanic ridges where the melting is close to the surface. This magma is punching across the plate, making a volcano, and as the plate moves, the hotspot remains in the same spot, and the volcano moves out of the place of magmatism, and the old volcano might be eroded and then fade into the deep ocean. So with all this data, there were two guys that put together the same kinematic frame, an American, Morgan, and a French, Le Pichon. Le Pichon started his PhD thesis with the idea of demonstrating that plate tectonics didn't work. So that's another lesson. You know, when you start your PhD with an idea, you might change on the way. You know? So that explains why he was 6 months late compared to Morgan. These guys were in competition, you know, and they wanted to publish as fast as possible their model, which is really a kinematic model that relies on identifying the plate boundaries, the motion, relative motion across plate boundaries, so divergence, convergence. And then when you have measured the motion of A relative to B and the motion of B relative to C, you can compute by vector addition the motion of C relative to A. That is what plate tectonics is. It's a kinematic model. And it's roughly the same. So the main hypothesis is that lithospheric plates are rigid. So if the plate is moving, I shouldn't do that. If you have the motion of one point, you have the motion of the full plate. That's very elegant mathematically. Plate motions are rotation about axis passing through the center of the Earth. So the plate motion is defined as a single vector of angular velocity. And relative motions are calculated by vector addition. So that worked fairly well. I made an exercise when I started to teach tens of years ago. I took the paper of Le Pichon and I tried to reconstruct plate motion with addition of vectors using his numbers. When you use his numbers, the Atlantic is closing. He made sign errors. And it tells you how fast these things were tried to be published and how bad the reviewers did their job. I was surprised. You know, it took me 3 years. You know, I did the first year. I said to the students, "Okay, used all nil, bad grades." Second year, the same results. Because I didn't do the exercise actually myself. I just gave it to the students. I thought they would give the right answer. 3 years after 3 years of having the Atlantic closing, I said, "Okay, I should do the exercise myself." I realized there was an error of signs. Even in papers that are foundations, you should be careful. You should be always cautious about what you read. I'm not saying that these guys were not honest. It's not a problem. They were too fast. And So that's a lesson also, I think. Not everything that is said in the book is right. So you should do your homework carefully, robustly, rigorously. Driving forces, so I'm not going to spend too much time on that. People have thought about convection, mental convection at different scales, only for the full mental, with different convection cells in the upper mental, lower mental, some kind of mixture of the two. Basically, mental convection might be a driving force for plate tectonics. Slab pull and slab push. We've seen in homes the idea that the density of the plate might also play a role by pulling, that slab pull. Ridge push, I think the term is not very good. The idea was that at first the magma could push the plate, but the magma pressure is not big enough, now we think, or we can calculate, to push a plate. So it's mostly, we'll see that in the next hour, it's mostly an uplift of the plate where it's thinned, and then glide by isostasy. But the ridge push term has remained in the literature. And then you have active rifting versus active rifting. Have you seen the nuance between the two? It's very different. Except that everybody's active. So active rifting for people looking at global scale, that means mantle and lithosphere, is this type of rifting. That means that here there's an upwelling from the deep mantle that causes uplift of the surface and then gravity glide of the topography. And it's active in terms of where the asthenospheric mantle is the main driving force. So the guys, mostly geophysics, talk about active rifting in that case. In this case, it's lithospheric, it's plate tectonics that drives divergence, thinning of the mantle, of the lithospheric mantle, upwelling of the asthenosphere that then feeds the process, and that's active rifting for these guys, looking at lithospheric plates. And for these guys, passive rifting is this. For the guys here, passive rifting is this. You'll find that in textbooks, be careful. Would you prefer to see yourself as active or passive? Well, it's the same for geophysics and geologists. Geophysicists think that this is active. Geologists, tectonics, think that this is active. Matter of terminology. If you use the same words to say, let's say, if we use different words to say the same thing, it might be confusing, but we might understand each other. If you use the same words to say different things, then it's getting very complicated to communicate. So the driving force for plate tectonics. So Earth, driving force, sorry. Yeah, the last one, so I came a bit onto it, is Earth rotation. And this, I think the fact that the Atlantic is really consistent with an axis of rotation, consistent with the axis of rotation of the Earth, is compelling. And this was killed in the egg in the 60s, and even before, people thought that this was not enough. And one or two teams that worked on that, Dolioni, from the 90s, worked really hard on that, and he really became paranoid because the full community was against him. Okay, you have strange ideas, And he said, okay, but there are asymmetries along plate convergence. There are plates where you have opening of back arc basins, and plates where you have no back arc basins, and you have mostly thickening of the crust. So I propose that there is an effect of relative motion between the lithosphere and the asthenosphere, or the deep mantle, that connects to that explains this asymmetry. So I will not go too much deeper into that, but I think there are many evidences that Earth rotation should be taken into account. And if you look at these type of projections rather than the ones that I showed you before, looking at this, of course, there is a huge bias because we represent a small surface as a very big surface, and there's big distortion. Here the distortion is much less important, and you see the Atlantic Ocean and the mid-oceanic ridge is almost coincident with the pole. Here the situation might be more complex, the South Pole, because the South Pole there is a strong continent here. So again, it's fairly symmetric here in the Indian Ocean, in the Pacific as well, it shows here, but then it tries to go around this strong nucleus, and that might cause some kind of discrepancy relative to the Earth rotation axis. So plate tectonics is really driven by dissipation of internal heat, which leads to gravitational instabilities, convection, gravity slide from the ridges, slab pull as the plates get denser along plate convergent plate boundaries, and Earth rotation. Okay, so that's plate tectonics. I see you taking notes. That's the history of plate tectonics. So now we're going to put orogenic cycle into that frame. I think you have all these slides, but it's good to take notes. I agree with you. You should take notes, and I also advise you to draw things. I made my little inquiry as a teacher, and also think about pedagogy. I see, it's not the case here, but my students in France, they now all have their cell phones taking pictures all the time of me and the screen. I say, are you sure you remember things? Oh yeah. And then I see the exams. Okay, I agree. Maybe I'm not a good teacher. You know, I take my part of responsibility, but I think it's very important to take notes. And I looked at the work of people doing how do you call that? How the brain works, and it looks like things are going from the hand to the brain. So it's important to draw things. I know myself. The first time I draw a tectonic scenario, it's difficult. It's not coming easy. And after I draw it several times, then it starts to make sense. And starts to be more fluent. I'm sure if you do that, you'll feel the same way. So I think it's important to draw things, to take notes, and even though you have the material, so it makes you feel more comfortable to say, okay, I've got time, but things that are important, take notes now. Neuroscience. Neuroscience that tells us that it's important to take notes. If you type on the keyboard, it works, but less than when you draw by yourself. So orogeny, how was it incorporated in the frame of plate tectonics? Well, at first it was subduction was followed by collision. When two continents would come into contact, that is called collision, and that's the end of subduction. That's what these guys, geophysicists, thought. And the rationale being that the continental crust is too light to subduct. So it resists subduction and it will stop subduction. And at the time, so I put that map again. Look at here. So I have to make a bit of zoom. Complex series of arc-like zones. What does that correspond to? That's the Alpine Himalayan belt. And the geophysicists, how do they describe it? Complex series of arc-like zone. Complex, well, that means that's difficult to understand. Arc-like, you're not really sure about what you're talking about. What it really tells us is that Mackenzie or his Isaacs and these guys, well, they couldn't make something out of the mountain belts. They couldn't make sense of it in the frame of plate tectonics. So it required the input of geologists. Dewey and Bird put the first compelling integration of orogenic belts in the frame of plate tectonics and defined two different types of orogenic belts, collision type belts, which qualifies for the Alps Himalayas, that are characterized by a period of oceanic subduction, with here some deformation of sediments, with sedimentation in a marine environment, and at some point the collision occurs, and the contact between the two continents would be marked by a suture zone, an ophiolite, which is here. But it's also characterized by these blue nappes, high pressure, blue schist, eclogites, high pressure, low temperature nappes, which means burial and exhumation. We'll come back to that later. And that's also marked by, at the surface, a transition between the flysch, which is now called turbidites, so deep marine sedimentation, to molasse, which is now called conglomerate, coarse-grained detrital sediments, continental sediments. So that means that there was an uplift of the surface from below sea level to above sea level, and that corresponds to the formation of the mountains. So this is all recorded in metamorphic, in geology, in sedimentary rocks by deformation and by metamorphism. And then they distinguish that from the coherent type belts, the peri-Pacific, where you can see also high pressure rocks, here in purple. But also there is a belt in more internal position of high temperature rocks. So high pressure and high temperature rocks, which in their model, they relate to here the emplacement of magma. So implicitly, they propose that this high temperature is related to contact metamorphism. And we talked about that, I think, with one of you guys. Say, okay, what is the input of granite, magmatism? So here they said, okay, that's probably what causes the high temperature, the rise of isotherms in this area compared to this area. But they also here invoke, without much describing it in the text, normal faults that are related to crustal extension. And you see these arrows. And that reminds a bit of the model of Scrope, you remember, with the magma going into the internal zone and the sediments gliding towards the external zones. I'm not sure these guys realize that, but they probably had that in mind. You know, everybody has some history, so you need to understand your history and where you come from, what is your background, and how it influences your ideas. Because this is not described in the text; it's represented in the picture, not described in the text. So at the time, there was also this idea developed for the Himalayas of indentation, rigid indenter, meaning that India was strong relative to Eurasia. I'm not sure if there's something political behind that, you know, but so you think about the strong India punching into Eurasia, and the consequence of that would be extrusion of blocks, Indonesia, China, South China, towards the east, localized along shear zones, continental scale shear zones. But what these guys first showed, and we come back to the indentation model afterwards, it showed that collision didn't stop convergence. Because this suture here can be dated. And it's dated at about 50 million years ago at least. So it means that collision between the Indian and Eurasian continent occurred 50 million years ago. And since then, India is still moving. Collision doesn't stop subduction. If we come back to that schematic representation, collision doesn't stop convergence. So I also here mention something important. You don't want to confuse plate kinematics, motion of rigid plates, that are measured far from deformation zones, with deformation, orogenic, tectonic zones. There you measure deformation, shortening, lengthening, and we come back to that tomorrow morning. So we don't want to confuse that. So collision is not stopping convergence, And at the time, the guys here made a clear correlation between plate convergence and crustal deformation, saying that the consequence of India punching into Eurasia is extrusion of blocks. And it was reproduced here with a metal indenter being pushed into silly putty with shear zones here localizing the extrusion of blocks towards the east, towards the free boundary, which is now the Pacific. I was a student, when I was a student exposed to that, I was saying, oh, I want to do geodynamics. It's fantastic, you know, with the silly putty and can reproduce the tectonic of Eurasia. It's fantastic. But then I had a closer look. What is here? These are bolts, nuts and bolts. And there's a plexiglass on top of that silly putty. Why did these guys put some plexiglass on top of the silly putty? Do you think they did that from the first attempt? Probably not. What happened to the silly putty before they put the plexiglass? Went up. Couldn't go down because it's on top of a plate, of a table. So it went up. But it was not what they wanted to show. So I said, okay, what if we want to show extrusion? Well, let's put a plexiglass on top. Then the silly putty has no choice than to go to on the side. So it was a bit disappointing for me as a grown-up now scientist when I realized that, because these guys were some of my mentors. But at some point you need to kill the father. At some point you need to, if you want to go beyond, you need to go to understand what was their bias and where you can go further. And don't take me wrong, this model was fantastic at the time. Even it was a bit biased, but they managed to show what they wanted to show, and it's been very influential. Maybe too much, because now most of tectonic plates or orogenic belts are explained by that process, which I think is not very compelling after all. But it's been very influential and stimulating. So what it also shows is that they considered here that the lithosphere is a single entity, and in zones of plate collisions, the lithosphere is probably thickening homogeneously, except that it's been dissected by lithospheric scale shear zones that allows for extrusion. And we come back to that. Oh, maybe I don't know if I'm not. No. So why this model? Because these guys worked also where there is an explanation. It was the onset of the use of satellite images. So they were looking at Asia and India from the top. Can you see up and down motions when you look from the top? No. So they couldn't account for that. But still, that's the place, the highest topography on Earth, And if you're not accounting for that in your model, you're missing something important, of course. But what they could see is offsets of rivers, offsets of sediments, offsets of geological features from the top. So they were limited by their technology, which was fine. It was very important to develop that at the time, in the 70s and 80s. I was a student at the time. I saw that development, and it was great to go from outcrop scale investigations to Earth scale. That's really what was allowed by that revolution. But at some point, you need to move further, and you need to take into account thickening of the crust and topography in this area. So what they did, they proposed that the lithospheres deformed homogeneously, but some other models were proposed, and that topography was, in that case, would be related to removal of the thick lithospheric root, dense lithospheric root, would pull down the topography, would be gravitationally removed, and boom, there will be a rebound, and that explains the topography in Tibet. That's how they got out of that dead end where they put themselves. But other researchers proposed that there was decoupling between crust and lithospheric mantle with subduction of the lithospheric mantle of the continental part, and they call that continental subduction. And this might lead to retreat and break off. These are the terms that were proposed, and delamination at the interface between the upper crust, the upper plate, and the lower plate. So that brings us to the present day paradigm. The lithosphere is subdivided into rigid plates that are moving relative to each other. And mountain belt formation in that frame is related to plate convergence, mostly, which brings magma from the mantle to the crust, and that leads to crustal growth of continents. And then there are different types of convergent plate boundaries that are involving either oceanic plates on both sides, and that's only growth of crust by magmatic processes. That's the case in the West Pacific for most of it. In the East Pacific, there is an oceanic plate converging towards continental plate, so it's adding some magma to the continental plate, but here mostly the mountains grow by deformation, shortening of the crust, thickening, that is then readjusted by isostatic rebound and leads to formation of mountains. And then there are collision plates with two continental plates that are converging towards each other. And we'll see that part of that lithosphere is subducting, part is forming the orogenic belt, and that's the alpine Himalayan belt. In that frame, mountain destruction is mostly invoked to be related to erosion and isostatic rebound, and the example here of the Alps, a young mountain belt, compared to a peneplain, here the Precambrian basement of Madagascar, but you can probably make the same picture of India with sort of a flat, rounded topography. And here the idea is that mountain building is resulting from shortening and the thickening of the crust, which with isostatic rebound makes a mountain that is followed by erosion, and the root is getting closer to the surface as material is removed from the top. And the Wilson cycle, in that Wilson being one of the guys that proposed that tectonic cycle, we can start anywhere, but we can start here with a continental rift that marks the onset of plate divergence. That leads then to opening of an oceanic basin, thinning of the lithospheric mantle. And then there is a switch from divergence to convergence that is accommodated by one plate being subducted beneath the other. And that's actually a question, where does it start? We don't have a good example of a starting subduction today. And it should start where there is a weakness in the lithospheric structure, but also where there is gravitational instability. So it might start either at oceanic ridges or along margins. And if we think in 3D, one good spot might be also the transform faults, because they are putting next to each other plates with different densities and weight. So that there might be also both a weakness in terms of mechanics and a gravitationally unstable situation. And then subduction leads to collision, mountain belt formation, and destruction by erosion. So we'll come back to that. That's a first order apprehension of the tectonic cycle, but there are some problems. So I move right away, right into these problems. So the next few slides, and then we take another break. So the first, and Malika has been working on that, is the generation of high pressure, even ultra high pressure rocks. These rocks are in a field, in a pressure temperature diagram that is much beyond the thickness, the depth of the maximum thickness crust. So that means if they are crustal rocks, that they were into the mantle. And now they have been sampled in Ladakh, in other places, in the crust, at the surface. So that means pressure is going this way. That means that they've been buried and exhumed. As if we take the model of tectonic accretion and mountain building before integration of these high pressure rocks, and even ultra high pressure, when we had blue schists, meaning pressure of the, let's say, equivalent of 40, 50 kilometers. With eclogites, it starts also to be on the edge of current day crustal thickness of 50 kilometers, 60 kilometers. But we can still explain it by just crustal processes, meaning that's about 60 kilometers. That's the Alps. That's the cross-section of the Alps where you have the European plate going beneath the African plate and tectonic units being accreted here to form the alpine wedge. And it's like a sort of a plane. But the plate is going like this, but there is some kind of buttress that doesn't allow the crustal units to go down and contribute to make the orogenic belt. So if you have rocks that are here now at the surface that went to 60 kilometers, the idea was that there was burial and then exhumation thanks to erosion. But if you have rocks that went all the way to here, that means that they have to go beneath the plane and then go up again. So I have to say, I forgot I was not supposed to be here. I should go back. That was quite complex in that frame. So there was another type of models that accounted for that, which is this continental subduction, meaning that both the lithospheric mantle and the continental crust, here represented in brown, was entrained in subduction, and that was reproduced with also silicon and sand in a big tank of honey analog models. And this guy managed to, it's a Russian guy, Shemenda, managed to drag the continental crust with the lithospheric mantle, but then at some point he managed to decouple mechanically the brown from the green, and that's related to the presence of this weak layer in black, but also to the buoyancy of the brown. The brown is less dense, more buoyant than the green. So at some point, which is this stage, the brown decouples from the green, and its main driving force is buoyancy that overcomes the mechanical coupling and the strength of the coupling between these two units. And in this model, he also has full erosion. He had a sort of a aspirator, how do you call that? Vacuum? No? Vacuum cleaner? What is the name? Suction, yeah. So he could erase as soon as this unit was coming up at the surface. He erased it, so it drove the system to have this point being exhumed all the way back to the surface. So it somehow explained how we can have these rocks buried down to depth and then exhumed back to the surface. It was also a very nice idea. So as first thing, we need to integrate in the Wilson cycle that was not in the first version. Second thing, extension of orogenic crust. Well, that was mostly identified in the Bayesian Range region of Western North America. In this area of desert, that's in the Whipple Mountains, in the Bayesian Range. And you see these more red units are actually volcanic and sedimentary units with the bedding like this. And they are in contact with gneisses and granites. And the contact is like this. Very shallow dipping, horizontal, with kinematic criteria that indicate a strong simple shear component in between the two units. And as the bedding is like that, that means that the bedding was horizontal to start with, so it's been tilted to its current day position. So these were called detachments and led to the definition of metamorphic core complexes. So at first, it was addressed by a kinematic approach with the pure shear, simple shear models of Mackenzie and Wernicke. Here, a pure shear model explains symmetric distribution of normal faults and in the ductile crust and the thinning, more horizontal, marked by horizontal layering of structures in the ductile crust. Whereas simple shear, there was a shear zone affecting the full mantle the full lithosphere, crust and mantle. But this was nice to distinguish between brittle and ductile deformation, but this was not really efficient at describing the full structure. Indeed, there is no such thing as a thinning of the crust localized in the Bayesian range. The Moho is flat. So it doesn't have this structure. The Moho is flat, is like this. And a more compelling model for that, to explain the diversity of structures is the one of Buck, 91, where he relates the style of extension, metamorphic core complex, wide rift, and even narrow rift, with the thermal state, which controls the rheologic, the mechanical state of the crust. So when the crust is hot, it has a thick ductile part and a thin brittle part, and this will lead to only limited faulting, only to the top part, and faulting will be associated here with flow of the ductile part into the space created by the normal faults. So that will result in tilting of the first normal fault, which was here. So it's been tilted, and that's been tilted is no longer active. It's no longer in the right position to be active. So another fault will be activated, which is going to be tilted as well, and so on. So the last fault is here, the one that is active, is at the right position to be active, and all the other ones have been tilted, and that creates a horizontal detachment. Very nice way to produce a horizontal detachment. The wide rift, which is the current day situation for the Bayesian range, with all these riddles, are host and grabens. It's explained by a less hot crust, so a bit more strong, with a thicker brittle crust, but some ductile crust, that redistributes deformation from one place to the other by flow, horizontal flow of that weak ductile crust beneath high angle faults. And this has been actually verified by a GPS monitoring of all the motion here on the Western North America, where they had put a network of GPS, and they could show that one fault was active here, and a few years later this one, and then this one, and then this one. So all these faults are active at once, at the same time, on the scale of a few years. You know? That means all that this area is undergoing extension, you know, but it's distributed over 1,000 kilometers. And then the narrow rift, that's when the crust is cold, very resistant. Normal faults are going all across the crust, and basically the distance between the normal faults allows you to identify the thickness of the crust. And that's what is happening in the East African rift, for example. So while in this zone where the Pacific plate converges towards the North American plate, is there extension? That was also a big question. You know? Nobody would expect that in this region. And by looking at the structure, the two-day structure of the Bayesian range, people realized that first the Moho is flat, and it's flat at 25 kilometers. And when geologists measured the amount of stretching associated with each of these normal fault hosts and grabens, they realized that it's been stretched by a factor of 2. So it was 50 kilometers to start with. So it was a thick crust. And the force then they evoked to explain that is the gravity force. So in zones of thick crust compared to zones of normal thickness crust of 30 kilometers, there is storing of gravitational potential energy, which is related to the difference in the weight between the highland and the lowland. The rho density, G, Z. That's the weight. So that's the difference of weight between here and there. And you can see it here. And that's the weight in the highland. So we go from a density of 2.7 of the crust to a density of 3.3 in the mantle. So here we have crust all the way around, up to this, down to this isostatic compensation level. Whereas here in the lowland, you go from crust and then change density from 2.7 to 3.3, boom, increase the weight. And these reached each other at the isostatic compensation level. And the purple, the pink area corresponds to gravitational potential energy stored in a zone of thick crust. And it was proposed that the formation here was related to a change between mountain formation related to plate conversions to destruction related to gravity. Gravity overcomes plate tectonics. We'll come back to that later on. But that was the first time it was invoked as a tectonic force, gravity force. And the last thing is exhumation of high temperature molten orogenic roots. So in many orogenic belts, and you know that from India, well, you find high pressure rocks, but you also find high temperature rocks. So that means that there has been a change in geothermal gradient from low to high. And myself, I worked a bit, that's where I come into play. Worked a bit on that because I started, as I told you before, in this Velay region, in the French Massif Central, that's in the central part of France. And all the pink are migmatites and granite. It's half of the map. So you cannot avoid it. It's the same in India, right? More than half of the maps are migmatites and granites or granulites. So what I realized at the time, this was the cross-section proposed by a guy from Montpellier, Matt. And you see here, basement, cover, basement in pink, cover in white, thrusts, duplicating the basement and the cover, and the domes. So this is a dome. Domes here expressed as antiforms, related to crustal duplexes, crustal thrusting on top of each other. Where are the migmatites? Well, migmatites are supposed to be here. Granites synchronous to deformation, plutons. Where do they come from? They are rooted in something that is rigid. There is something that is problematic here. And most of all, I think I'll come back to that later on, this problem, but another thing I want to show here is in order to have these rocks, which were metamorphic at the time of orogenic evolution, which was corresponded to about 15 kilometers depth, that thickness. In order to put them back to the surface, you need to remove this rectangle. And the only sediments that are identified of that age are here and there, these small gray things, the upper Carboniferous basins. And you need to put, these are the gray triangles. So in order to exhume these rocks by erosion, you need to put the pink rectangle into these gray triangles. You see that obviously it's not going to work, right? You can push hard, but it's not going to fit into these small triangles. And especially the sediments are less dense than the metamorphic rocks. So it's not even pushing is not going to be a solution. So how do these rocks being exhumed? And I can come into play. That's me in 1990 something. Sorry, I'm getting old. I discovered the apple at the time, so I was happy. And I changed this cross-section during my master study. First I realized that we worked on that project, so it's a zoom of this structure, the Velay dome. And it's really a dome. It's delineated by structures, by lithologic units that are surrounding this zone. And it was part of a mapping project which involved about 10 academic centers in France with different people working on different rocks. People from Clermont-Ferrand. Clermont-Ferrand is in central part of the Massif Central. They are specialists of granite and plutonic rocks. And they were mapping granite. As long as they could see granite in the rock, they say granite, 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 granite. People from Montpellier, southern France, specialists of metamorphic rocks. They looked at schists. And as long as they could see schists in the rocks, they map it as schist. And this is 20 kilometers. And the first field trip we had together, the discrepancy between these two contacts, granite and schist, people from Clermont-Ferrand put the contact between granite and schist here, people from Montpellier put the granite and schist contact here, 20 kilometers difference. Okay, wow. I was a student at the time, or a master student. These guys don't know what they're talking about. They don't agree on the name of the rock. Well, in between, the rocks are migmatites, a mixture between granite and schist. And it was a difficult problem. You know? And these migmatites, they look like this. So you have a part that is gneissic, a part that is granitic. Some would look at this part, some others would look at this part. And no one would consider the mixture. They have a foliation, which is okay for structural geologists. It's difficult because it's not as well organized, but still there is some kind of preferred orientation, so a foliation, which we'll see tomorrow is recording orientation of solid parts in the magma, in the melt, at the time of coexistence of the two. So it records deformation in a partially molten state. The guys from the schist said, okay, no, that's inherited structures from the potolith. So we pretend the granite is not there. We just measure the structures in the schist or the gneisses, and we pretend the granite is not there. The guys from the granite said, okay, granites have no preferred orientation, so that's not an orientation. No, granites, magmas are isotropic. Well, okay. And this foliation, when you measure it, is concentric. And the difference in distance between this point and this point is 100 kilometers. It's from here to there. 100 kilometers. So I tried to do the first cross-section of this area, and I realized, wow, this dome is 3 times the crustal thickness. This has to be a crustal scale process. It's not something that is just a granite coming from nowhere. And Matt is describing that granites are kind of disturbing the picture. So we try to avoid them, not to see the real rocks, the ones that are important, the metamorphic rocks. So, well, if you make that, you miss half of the story. So I transformed that section like this and considered that all these migmatites are crustal scale. And here, I think you feel the ductility, the flow of these partially molten rocks that will rise up and form domes, in different parts. So we'll deal with that tomorrow morning. That's for Malika. Who was next to me? Michel. We've been, that's a friend of mine. We've been close friends since the first year of study. And he was visiting here in 2018. Malika has come also to visit in Toulouse. So that's the other lesson. When you choose friends, be careful. Huh? It's going to last longer. If you meet people in your studies, make sure you choose the right ones. Okay, so that's the second conclusion, the conclusion of the second part. So if you want to understand the evolution of mountain belts, we need to integrate results such as high pressure rocks, migmatites, extension of orogenic crust, that will allow us to address the question of transition from low to high geotherm, the transition from crustal thickening to crustal thinning, and then the process of exhumation of metamorphic rocks. And you want to really be careful to distinguish plate kinematics, the motion of rigid plates, convergence, divergence, from deformation. Deformation is shortening, lengthening, so that's the scale of rocks. And then crustal deformation, and that's the terms that are the most confusing, is extension. I think tectonics people mean crustal thinning. Compression, where they think of crustal thickening. But the same terms, compression is used for plate, so for mechanics. I don't know if you have rock mechanics, but rock mechanics is trying to make the link between strain and stress. And stress is called compression. We used one term to describe two things. Lots of confusion in the literature. So if you think you don't understand these papers, it's not your fault. It's because there is confusion between physics people, rock mechanics, and tectonics. Extension and compression are terms to be very careful with. So distinguish deformation from dynamics and from plate kinematics. And then we'll look at the force balance and at the thermal balance, the thermal evolution, but we'll develop that later on. And we'll integrate from lithosphere to grain scale, and we'll look at the mechanical behavior. We integrate metamorphism and magmatism and deformation, and we also, as an observable, look at the evolution of topography, which is going to be the next hour. So another short break, still have some energy. You're the timekeeper.
In this tectonic setting, we may found retrograde metamorphism.
Everywhere. Actually, most of the metamorphism is retrograde. It's more difficult to keep a record of the prograde. So let me see. That's a good question. I would say that you have more chance to keep the prograde path where you have lower temperature. So in this type of path, you have burial exhumation. If you have this and then increase in temperature, and we'll see that in the next few days, then it tends to erase all the former history. If the rock melts, the minerals that were there during the prograde metamorphism are no longer there. They've been molten, or part of the melting reaction. So they lose the record of the prograde. So we'll mostly have the cooling path, the retrograde path. Is that your question? More or less. Huh?
No. So you were explaining about the orogenic settings. So one plate goes deeper and then it comes again.
Yeah. So that's what the retrogression.
Yeah, that is retrogression.
Yes.
So you were talking about arcs.
Yes.
I thought that there will be a commonly found in retrogression.
Yes. Exactly. We'll see that.
But there are no, like in the other tectonic setting we don't found the retrogression.
No, I think you do. You do. We'll see retrogression in almost all tectonic settings, but not all over the place. That's fortunate. Then that gives us the opportunity to study different stages of orogenic evolution, but that from rocks that are different structural levels today. The part that are on top might have preserved the high pressure rocks, the part at the bottom, the high temperature ones, and all of it, the retrogression part of it. But we'll come back to that, I think. But that's a very good question. I might have to think about it when I go through the lectures tomorrow and Wednesday. There was another question. Yeah.
I didn't get the compression and
Extension. So compression. So the term is used in mechanics and in tectonics. For tectonics, compression means crustal thickening, and extension means crustal thinning. But compression, the term is also used in mechanics, and we'll see that tomorrow morning, where people try to relate the stress and strain. Stress, you see, it's I don't know which term you use, but which symbol you use, but you used sigma. Sigma 1, sigma 2, sigma 3, and you probably learned that at some depth, the state of stress is in triaxial compression. Compression is also used in tectonics. So the mechanics guys say, okay, we are in compression, to say that there is a triaxial state of compression. All the sigmas, the main stress axes, are positive. That's compression. So that doesn't mean thickening or thinning. Okay? As for the tectonics guy, compression means thickening. For the mechanics guy, tension means that one of the stress main axes is negative. It doesn't mean thinning. So tension, extension, confusion. And we'll see tomorrow, that today in the Alps, there are thrusts in the front, normal faults on the top. And it's at the same time. So a structural geologist in the foreland would say, that's compression. Normal fault, tectonics guy in the internal part would say, it's extension. They are both right, but inconsistent. But we'll see. It's just to tease you. We'll see that tomorrow, the explanation of that. Actually, not tomorrow, the day after tomorrow. Just one.
So what are the possible or favorable conditions to form
Just
migmatites?
a bit louder.
What are the possible favorable conditions or tectonic settings for migmatites?
For migmatites, well, we'll see that tomorrow as well. But it's mostly, for the short answer, it's a zone where the crust has thickened and remained thick for 20, 30 million years. So that's one possibility, but I see you coming. It's probably not the only possibility. For Phanerozoic, that's probably the Phanerozoic is the recent mountain belts. That's the condition, is that the crust remains thick for 20, 30 million years. For the Proterozoic and even the Archean, where in a Earth that was hotter, the crust was not needed the crust to be that thick. Maybe thinner is enough. But the lithosphere might also play a role. So we see that in the next coming days. Very good questions. And that's also precedes my lectures. Which means I was a good teacher, because what you should do as teachers, I think, is to make the audience feel smart, so that they ask questions even before you provide the information.
I was just wondering what kind of alteration we might see when exhumation happens. Because now these rocks were at a particular depth at that point of time. And as soon as they ascend, because of the change in temperature and pressure and all of that, there can be some alteration.
Yeah, alteration.
So how are they actually preserving that past temperature and pressure?
Obviously,
What
yes,
kind of-
because we can study them. But it's a good question, and that comes to the same question with retrogression. How much the fluids interact with these rocks as they exhume, and
So how much are they actually reflecting that
They are-
metamorphic
yeah,
past that
yeah.
we are trying to
No, that's a tricky one, and you need to do extensive field work to identify the right samples to investigate both, because both are happening, right? When you collected your samples for ultra high pressure, probably most of the rocks were retrogressed around, or not.
Sorry?
When you studied your rocks with the ultra high pressure,
Yeah,
probably most of the other rocks around were retrogressed.
yeah, they were all retrogressed.
So you have to find the right one.
We had preserved the.
So I need to take a certain number of samples to actually say that this is what actually happened. In
More
terms of the-
than taking a certain number of samples, you need to actually do extensive fieldwork to see where exactly is the prograde signature preserved.
Yes.
And that's probably more preserved in the minerals rather than in the whole rock.
I think that also relies to structure.
Yeah,
No,
that's also-
if you, the place where you identify the earlier structures, the ones that are less overprinted by the later ones,
the later ones.
then you have the best chance to have the.
So it won't be wise if I just take a single transect.
No.
and-
Yes, you can do a transect, but not random sampling.
Can't be done.
No, you do your structural analysis. I mean, for me, lithologic units, structural analysis, petrology, then some geochemistry, some geochronology, but only if you have done all your homework before. Otherwise, take big risks.
Yeah, I had a question on that metamorphic core complex that diagram you showed. So you made that shear zone,
Yeah,
which is
Shallow, yeah.
clean. Apart from that, there are
these are preserved. Yeah.
So what is happening on the surface? Whether they are related with the transformation as well?
Yes, yeah, very often, and actually we'll see that in very briefly on the Aegean part. These shallow detachments might be even folded, and they have what we call corrugations, but they be flat, but then folded by the second order structures, and that's very common.
So then, I mean, to say that there is...
And then there are transfer folds in between.
Yeah.
Yeah.
So is there a possibility of having a crustal scale flower structure kind of?
Yeah, I see what you mean. Oh, yeah. Yeah. I won't show that type of examples, but yeah, I see what you mean. Yeah. I think we might see some.
Okay.
I was not going to insist on that, but yeah. I can't because I.
I have one more question. Is there any particular geothermal path for the formation of migmatites, or it just follows the...
Yes, you need. You can have migmatites, either high pressure migmatites, that's granulite facious migmatites, or eclogite facious migmatites, mid pressure migmatites, and low pressure. So these are the conditions of the migmatites, and we'll see how this goes into the tectonic scenario. No, these are all good questions. I'm not. So that means I put all the good seeds in your brains, and now for the next days we'll answer part of these questions. Probably not all of them, but part of them.
So Oliver, the next lecture is how long?
About half an hour, 45 minutes.
So do you want to continue? Because
I don't know. How do you want? Or do you want to take a short break? Or what is time? How is it time wise? Stop.
अच्छा मग ते आता ते एक शेवटचं लेक्चर राहिलं त्यांचं पण ते ब्रेक नाही घेणार मग Just
Continue?
because the streaming stops, I told you, right?
Ah, okay.
So we have to make-
I was too long for the second part.
Sorry?
The second part was too long.
No, we should probably just manage time better next
Okay. So I'll do it. The short version of that third part is lithosphere definition and earth topography. So we've seen that with barrel we have the identification of lithosphere as being relatively rigid compared to the asthenosphere, relatively weak, soft. That's been also shown in that picture. So let's expand on that definition, first definition. So in terms of seismic waves, these are S waves and P waves, primary and secondary waves, with the velocity here in kilometers per second. And geophysicists identified that these waves increase in speed from the surface and at depth until a depth of about 150 kilometers, whereas there is a decrease in velocity propagation. So that's a low velocity zone. So that's another way to define this lithosphere-asthenosphere boundary. And why this low velocity zone? Well, one possibility is that at that depth, the geotherm, which is the increase in temperature in degrees Celsius as a function of depth, is reaching the solidus of peridotite, the rocks that make the mantle. And that here the solidus, that means the first occurrence of melt in the rock. And the presence of melt is going to attenuate seismic wave propagation. So that might be an explanation. In terms of mechanics, that's here represented in megapascal, the strength of the crust and the mantle as a function of depth. You see that there are two different ways to express the mechanics, the strength. Either a linear increase in strength as a function of depth. And at some depth, there is a decrease in the strength that is parabolic. So maybe that's a part we can skip. I'm not sure who was exposed or not to rock mechanics. Everybody was exposed to rock mechanics or not? I can spend 5 minutes on that. So so you're not sure? I do it? Okay? Yeah. So that's stress, sigma, and strain, epsilon. So it's 1D stress-strain relationship. And rocks typically have, when they are submitted to stress, they have responded. The first response is an elastic response. It's not that big, but it's recorded by deformation. Elastic deformation is reversible. That means that if the stress stops, the rock recovers its initial state. And at some point, there is an elastic plastic transition, which corresponds to this yield stress, which is the elastic plastic transition. Plastic deformation is not reversible. It's forever. And rock typically then have a behavior where plastic deformation increases with increasing stress, with more stress being required to deform and so on. And then at some point, rock rupture. So that's a catastrophic loss of strength of the rock submitted to stress. That's a typical behavior. What is controlling this different state of strain? So pressure first. For pressure, with the pressure increase, that controls the transition from elastic rupture to elastic plastic ruptured and then elastic plastic. And the way I explain it, with the hands, is related to, so pressure is the depth of the column, of the rock column. So it's related to confining pressure. So if you put much pressure between your hands, it's easy to move. If you put a lot of pressure, difficult to move. So that's this effect that we measure here. Confining pressure. Temperature. Temperature, at low temperature, there is elastic, and then rupture. And at high temperature, you go from elastic to plastic without rupture. What does that express? Temperature, also with the hands. I'm a physics guy with the hands. I'm not really good at math. And with temperature, will allow atoms to be excited, and they move as temperature increases. They move more, so it's easier to switch place with the neighbors. So this calls upon a process that is atom scale. This is rock scale. This is atom scale, the ability of atoms to move into the minerals. And that controls plastic flow. As has been measured in laboratory, the brittle behavior, putting rock into a press, Byerly is a researcher that's allowed to identify the shear stress, normal stress. So that's the confining pressure, and that's the deviatoric stress. That's what controls deformation that is correlated to the weight of the rock column. And it shows that for any rocks, if you take a gabbro, a basalt, a granite, you have the same behavior with increasing strength as a function of increasing pressure. And it's almost linear. This is this part. And it doesn't matter if it's crust or if it's mantle. And then the other ones studied rocks at high temperature, and they identified that the flow law, so the strength as a function of temperature of quartz, here in orange, is different from the flow law of olivine. Quartz is the main mineral of the crust, olivine the main mineral of the mantle. So these are different. And they describe a decreasing strength with increasing temperature. And this is this part. So that's the law for olivine. And as the temperature in the crust here is not high enough to activate the flow law and the temperature of the crust, it's only here at that depth that it's activated. In the continental crust, continental lithosphere, you have the brittle behavior, which is related to confining pressure, both in the continental crust and in the lithospheric mantle. And there is here part of the continental crust that behaves, which behavior is controlled by flow of quartz activated by high temperature. And then flow of olivine activated by temperature here. So that means you have to have, well, first, that this low strength might correspond to the transition from lithosphere to asthenosphere. So without the need to call upon the presence of melt. Maybe just the high temperature deformation of olivine is enough to explain this low velocity zone and define the lithosphere-asthenosphere transition. I come back to the continental crust, the lithosphere, sorry. There is a weak zone here, but there's also a weak zone here. So we'll come back to that in the lectures tomorrow. How important is this weak zone in tectonics and the construction of orogens? The definition of the lithosphere is here by density, so it's controlled by chemistry of the mantle, and this mantle has a history of extraction of melt, and it changes its density, and at first approximation it's not that well defined actually, but it should be more dense than the asthenosphere. And there's also then the kinematic definition of the lithosphere that makes plates moving relative to each other. So, in short, we have lithosphere which is defined mechanically to be strong, thermally to be conductive. Oh yes. So when the rocks are strong, then it's not easy to deform. So heat is mainly transferred by conduction in these rocks. Whereas in the asthenosphere, that's the computation of Holmes that I showed earlier, it's possible that the mantle is in convection. So then heat is transferred by advection, not by conduction. So it's thermally conductive, chemically dense, and it's also kinematically identified compared to the asthenosphere. And all these characteristics, that's what controls plate tectonics and mantle scale mass redistribution. Okay, now, so that's the definition for the lithosphere. Now, how do we integrate the topography? So first we have to identify what is the behavior, the fate of the lithosphere along convergent plate boundaries, whereas it thickens homogeneously with the crust and then thins by gravitational instability, or whereas it behaves differently with homogeneous thickening of the crust and decoupling from the lithospheric mantle, where the lithospheric mantle is subducting. Seismic tomography has shown that most of plate convergent settings are associated with a blue zone that dips into the mantle. And this blue zone is a high velocity anomaly, which geophysicists interpret as being a plate. So most convergent, if not all, convergent plate boundaries are associated with subduction on one plate. Some are also associated with collision belts, some without collision belts, and this will be tomorrow's lectures. So it's mostly this behavior that we see. Not much this one. Which doesn't preclude this to be pertinent for the past. Maybe the Archean and the Proterozoic. But at least for Phanerozoic, we know that this is the dominant situation. Earth topography. When you compare to the moon, what characterizes the Earth topography? Well, if you look at the moon, it's full of impact of meteorite craters. Do you see them on the Earth? Why isn't it the case? So I'm asking that to my first year students, and I identified a change in the answers since the last 10 years. So I'm curious to see what you have as an explanation. Why we cannot see meteorite craters on Earth? They say the same. But 10 years before, they didn't say that, with the idea that the atmosphere will stop the meteorite. You know, the stars, how do you call that? The light that is going across the sky. What is the name for that? I don't know the English name for that. Comet. No, but the ones the one that goes across our atmosphere. They are small meteorites. They are not even very small, and you can see them penetrating the atmosphere. Do you think that the one that is causing a crater like this would be stopped by the atmosphere. No way. It's going to be creating lightning, light, by heating, but it's certainly going to go through. No, that's not the main process. Main process is activity of the Earth. The internal cycle, the external cycle, erosion, due to presence of water, and plate tectonics that renews the Earth's surface, constantly. Continents are made of plains, mountain belts, basins, oceans of abysses, ridges, and trenches, and this reflects Earth dynamics, redistribution of masses owing to internal and external processes. And the Moon is not a dynamic planet or body. The Earth is. Probably started like that, but all these craters have been erased from the surface of the Earth, all or most of them. So if we go a bit further into the Earth topography, you see that there is a big difference between continents and oceans. This is the altitude relative to sea level, taken as 0, and in classes of 1 kilometer, 0, -1, -2 kilometers, +1, +2, +3, +5. And you see the Earth's surface in percent that corresponds to each of these classes. So you see that there is a maximum for the continent that is between around 1 kilometer, so with an average of 800 meters. An average for the oceans that is at 4 kilometers depth, and there are two bell curves around these two maximum. So that means that probably the continents are distinct from the oceans. And this was identified by Wegener as well, at the time of continental drift. So let's start now with the topography of the oceans. So this is the age map of the oceans, and compare that with the surface heat flux map reconstructed from surface heat flux measurements. What is the correlation? So as I'm doing it short, I wanted to ask you questions here, but I need to speed up a bit. We can see that there is a correlation between the zone of high heat flux, that's 600 milliwatt per square meters, and the oceanic ridges. Oceanic ridges are zones of high topography in the oceans, which are zones of young crust. Oceanic ridges are zones of young lithosphere correlated with high surface heat flux. Oceanic trenches more or less corresponds to zones of old lithosphere that's very marked in the West Pacific, and it's marked by low surface heat flux. So there is a correlation between all these parameters, and this was calculated by Sclater in 1981, that there was this decrease in heat flow as a function of distance from the mid-oceanic ridge and as a function of age. And he reproduced that by a cooling model. So, in other words, as the plate diverges from the mid-oceanic ridges, it cools. That's an isotherm, which is about 1350 isotherms. That becomes deeper and deeper, and when the mantle cools down, it becomes more dense, then it will subside, lower the topography. Ocean's topography is correlated to lithospheric thickness. As the plate diverges, the lithosphere thins and then uplift. And as the plate diverges from the ridge, it thickens, becomes heavier, and goes down, subside. Up to the point it's gravitationally unstable and boop, falls down into the deep mantle to make subduction. Okay, that's first conclusion. Oceanic lithosphere controls, the thickness of the oceanic lithosphere controls its topography. What about continent? So this is a map of crustal thickness that was compiled in 2000 by Basins et al. And you recognize what the main mountain belts are correlated with zones of orange, which corresponds to thick crust. So in mountains are correlated to thick crust. What about surface heat flux? You see that, so here it's a different scale from the other one. It's only going from 10 to 100 milliwatt per square meter. And you see a zone here, purple and red, that corresponds to Alpine Himalayan belt, but also here to the North American Cordillera and South American Cordillera, which is all red, so meaning a high heat flux. Why is this high heat flux along mountain belts? I remind you, high heat flux in the ocean corresponds to thin lithosphere. For the continents, thick crust. Yeah, it means high temperature. Huh? High temperature.
The lithosphere is conductive, so it may conduct more heat, so that is why.
If it's conductive, it's actually insulating. The heat is better transferred when the conductive layer is thin. The more conductive, the less heat will get from the Earth's interior. So it's the other way around. It's not a problem, but it was a good idea. We'll come back to that. So there's something missing. The continental crust is concentrated in radiogenic elements, uranium, thorium, potassium. So the thicker the continental crust, the more heat will be produced by these elements, and the hotter it will be. And this comes to the time scale that is required for having a high temperature crust after thickening. It comes to the time of heat conduction and the timing of heat production. And these takes about 10, 20, 30 million years to be efficient. It's not right away. If I take you and I put you at 150 kilometers, right away you'll feel the ultra high pressure. It's instantaneous. But the high temperature will take 30 million years. The time of conduction, the time of heat production. But we'll come back to that. So, okay, possibly thick crust corresponds to high thermal heat, surface heat flux, but there's also high surface heat flux in the East African Rift. How do I explain this high surface heat flux? Rifting. Plate diverge, and what happens here? The lithosphere thins. So here, the high surface heat flux is explained by thin lithosphere. High surface heat flux here explained by thick crust. So we don't really know if here we're looking at an effect of thick crust, or we'll see. So let's first order observation. Thick crust, high surface heat flux. Rift, thin crust, high surface heat flux as well. So we have two explanations for high surface heat flux. So at first, surface topography in the continents was explained by isostasy. Mountains were identified by gravity data to be zones where excess of mass related to the mountain is compensated at depth by the deficit of mass. And this was actually, at first, it was a disappointment. Bouguer, who measured that in the Andes, he thought he could find a difference in mass related to the mountain, but he didn't find anything. So he was really disappointed. Actually, he described all this, but didn't find the model. The model came from these guys, Pratt and Airy, same year. One who stipulated that the zone of thick crust, the mountains, are related to low density material compared to the lowland where there is higher density. And that at some point, the excess of mass, because of the low density here, is compensated, and the pressure of this rock column is equivalent to this rock column at the isostatic depth compensation. This other model says that, okay, no, the crust has all the same density. It's just that beneath mountain belts there are thick mountain roots. To explain that at some compensation level, the pressure beneath the mountain belt is equivalent to the pressure beneath the lowland. And taking a density of 3.3 for the mantle and 2.67 for the crust. So that's this model. And it follows Archimedes' principle. Any object totally or partially immersed in a fluid or liquid is buoyed up by a force equal to the weight of the fluid displaced by the object. So it means if we put the compensation level here, that means that the pressure in A is equivalent to the pressure in B. This is the crust, this is the mantle. What is the behavior of the mantle here? Where is the mantle in Archimedes' principle? You have it. Which part is it? Is it the object that is immersed, or is it the fluid? It's the fluid. What did I tell you about this mantle in terms of mechanics? That's the strongest shell of the Earth. And we are pretending it's a fluid? That's a big mistake here. It works. At first order, it works. But there is a big bias here. You can do that. That's exercise also for an exam, Malika. I provide exam for Malika. That's also something you can calculate. PA, pressure in A and pressure in B, considering the weight of the column rho G H. And you can compute the thickness of the root compared to the thickness of the topography, taking a normal thickness crust as a reference. Yes, so that's the last thing I want to show you before lunch. So this compilation of Artemieva and Mooney, they compile all geophysical data that allows to identify the thermal lithosphere and its thickness in kilometers, from 40 kilometers to 350 kilometers. What does this picture show? Well, first we see all the blue spots, a thick lithosphere, corresponds to old cratons. The Superior Province, the West Africa craton, the Scandinavian, Siberia, somehow India, West Australia, South Africa, the Brazil. We see all the cratons. And they are related to zones of low surface heat flux. And that's because of the thick conductive layer that impedes heat to be transferred. Right? It's insulating. Matches? Right? When the lithosphere is thin, convection is very efficient at transferring heat. Look at what happens in the Alpine Himalayan belt. Red and orange. A lithosphere that is 40, 80, 100 kilometers thick at most. Lithosphere. So if you take out 50 to 60 kilometers thick crust, it only leaves 20 to 30 kilometers for the lithospheric mantle. So in zone of thick crust, for the Alpine Himalayan belt, the crust is thick, the lithosphere is thin. We have a big paradox here that we're going to resolve in the next lectures. So if you take that into account, we don't know if most of the high heat flux identified here correlates to thick crust producing a lot of heat by radiogenic decay, or thin lithosphere that promotes transfer of heat by advection, and maybe both. So in other words, same for the topography. How much does it relate to thickness of the crust? So a thick crust will promote high topography. But a thin lithospheric mantle, what does it promote in terms of topography? Thin lithospheric mantle, uplift. So if we want to understand continental topography, we need to consider both the thickness of the crust and the thickness of the lithospheric mantle. So this leads me to my conclusions. So I'm not going to go through that. I'll leave that also. Yeah. Let me see. So the topography of the ocean is controlled by the lithospheric thickness. The thicker the lithosphere, the lower the topography. The topography of the continent is related to the crust lithospheric mantle ratio. The thick crust promotes high topography, but if it's associated with a thick lithospheric mantle, that would counterbalance the effect of high mountains and lower the topography. If a thick crust is related to thin lithospheric mantle, this will increase even the surface uplift. And in rift, it's both thinning of the crust and thinning of the lithosphere, and you also have a counter actions of these two processes. And I'll leave you with that slide that introduces the lectures of tomorrow. What about topography in zones of plate convergence? So I just did that with Google Earth. I did the sections across convergent plate boundaries, and you can easily retrieve the topography. So I did that for orogenic wedges, zones of mountains with a triangular shape. Wedge is a shape. A wedge is a triangle. So I did that Taiwan, Papuasia, Ecuador, Patagonia, Pyrenees, Alps, all roughly triangular. Oh, by the way, by topography, I do not mean morphology. I leave that to geomorphologists who are studying erosion and surface processes. Topography is the first order shape. That's this shape. And then it's been eroded a little bit, valleys and peaks. That's morphology. So you have triangles, but you also have rectangles, what we call orogenic plateau. Altiplano is one, Tibet is another one, and there's also one in Anatolia. In Turkey, there's another plateau. And more surprisingly, there are intermontane basins. The basin and range that I talked about, but it's also the case in the Pannonian basin between the Dinarides and the Carpathian, and also in the Zagros, you have basins, low topography, surrounded by high mountains. So that's surprising. And if we look at the altitude difference between different orogenic wedges, as a function of width of this orogenic belt, all the squares here are the orogenic wedges in green, and you see that there is somehow a correlation between altitude and width, up to something about 5,000 meters, and thereabout, there's no longer a correlation between altitude and width. This corresponds to the wedge plateau transition. What limits the altitude of orogenic belts? What controls that transition from wedge, from triangle to plateau? So this is tomorrow's lecture. You have the night to think about it. Okay, I'm done. I think so. Yeah.
Stop. If you have any questions, we can ask.